For this project, we did all of our code using Python under PyCharm IDE. We used these four Python libraries: matplotlib, plotly, numpy, the BFS algorithm, and the A* algorithm. We put them into Python and then into the JuPyter Notebook. The following is a demo of our project on JuPyter Notebook.
So, as part of the upcoming Artemis mission, NASA released a large satellite dataset of the lunar South Pole, which was the area around the Lunar Module landing site as well as the exploration site near the Shackleton crater. And while designing the rover, it's important for them to understand the minimum power the rover needs or the amount of slope it can overcome to navigate the terrain. And a rover with higher power can increase the cost significantly. And so we wanted to develop an algorithm that will automatically find and map the shortest possible path between those two coordinates when given the slope that the rover can overcome. So when we were given the large lunar data file, we first tried to understand what was in it. And what was in it was 1.5 million lines of latitude, longitude, slope, and height data between a specific range of coordinates of latitude and longitude. And the problem was that the file was too big to plot, it wasn't sequential, and it wasn't equally spaced, so it couldn't have been used in the maze. And the data was also in spherical coordinates that needed to be converted to Cartesian coordinates for plotting it. And here, this image is an example of what the 1.5 million lunar data plot file would be in the south side of the moon. Here, this is just showing the difference between the XYZ Cartesian coordinates versus the latitude, longitude, radius of the spherical coordinates. And here you can convert circle to Cartesian, and this is just an example. So the first step we had to do was to create a sequential, equally spaced, and reduced matrix file that we could use for plotting and for the BSF and A* algorithm. And so what we did is that we had the original 1.5 million point data file, and we created two files off of that. The first one we did is that we first selected an area around the landing and destination site, which gave us a better resolution for wayfinding, and we converted that to a 300 by 300 circle zoom matrix, which is around 90k points. And how we did that is that we used the latitude and longitude coordinate range and created 300 equally spaced coordinates in that range from the 450k file. And since the coordinates weren't the actual coordinates from the original file, we looped through both files and compared and found the nearest lunar coordinate, 1.5 million data coordinate point, for each of the zoom matrix coordinate points. And we used those. And then after that, we just ran the BSF and A* algorithm for the maze. And for the other one, we converted it to Cartesian. It was the same amount of points, but we did that so we could complete terrain, so we could have a complete terrain for the points. And we converted that also to a 300 by 300 matrix. It was basically the same method, and we plotted that. And here we are just going to compare some graphs that were made. Here is the original 1.5 million data file point, and this is the 300 by 300 one. As you can see, this is a little bit less detailed, but you can still see both pretty well. And here is the other one. And here we have the spherical ones. So here's the original 1.5 million data point, and what we did is that we just cut out the rover path and we converted that to spherical, and this is what we got as a result.
This is the rover wayfinding using the BFS and the A* algorithm. So we started with the 300 by 300 spherical zoom matrix, which was 90k points that we got from the NASA file, the original NASA file. And from that we create go cells and no cells. So for example, if the rover slope is 15, then the go cells will be slopes below 15, and the no-go cells will be slopes above 15. So then we create the maze 2D table and the landing and the destination index so that we can feed it into the BFS algorithm and the A* algorithm. And they traverse through the maze, and then it generates a rover path of indexes. And after that, it converts the path indexes to latitudes and longitudes from the 300 by 300 spherical zoom dataset. And then from that, it generates the rover path file. So both the breadth first search algorithm and the A* algorithms are used to find the shortest path between the start and the end points in a maze. So for the BFS algorithm, it creates nodes and then it traverses all paths simultaneously and then finds the shortest possible among the paths. So for example here, it starts at A and then it's trying to get to B. So it will create nodes whenever there are more than 2 or more directions to go. So there's a node here, and then it'll go this way and this way simultaneously. So when it goes this way, it'll bring us to another node, and then it'll go this way, and it'll realize that this is the end of the matrix file, so it'll stop the algorithm here, and then go back to this node, and try it this way. And then it'll realize the same thing, then end that, go back to this node, and then it realizes it's tried both of these ways, so it'll go back to the previous node, and then it'll continue this way. So it does this until it gets to the end of the maze. With the A-star algorithm, the A-star algorithm is the informed or the directional algorithm that always moves towards the target, and typically A-star is faster, but it depends on the maze. So the A-star method also starts at point A and goes to point B, but instead of finding nodes and creating a path like the BFS algorithm, it will find points and then it will calculate how far those points are to the end, to point B. And it will find the shortest path to it, and then it'll go through that pathway to go to the end. So now we can look at a rover path example. So here we have a rover path example, and on the y-axis we got the longitude in Cartesian coordinates, and then on the x-axis we have the latitude in Cartesian coordinates. Now this is the slope between the latitude and the longitude, and the yellow cells are slopes below 15 and the blue cells over here are slopes above 15. And as you can see, the rover goes from the landing point to the destination point, and it goes through all of the yellow cells to get there. So here we can see that we're setting the slope to 14 and 15, and when we hit the compare path button, we get these two graphs. So with this one, this is the 14 slope one, and you can see that it stops here because there aren't enough cells or yellow cells, and the path gets blocked. And then when we go to 15, we can see that we are able to form a path, and it's a little bit long. Now when we go to 18, we can compare that here. We can see that the path gets shortened from the 15 slope one, and when we do 20, we can see that the path is almost a straight line.
The terrain was plotted using a Plotly mesh plot that represents the three Cartesian coordinates of latitude or x, longitude or y, and height or z. The rover path was superimposed on the 300 by 300 matrix file, and the colors represent different heights, with the Shackleton crater at the center. And here is the graph. You can see the different colors represent different heights or z's, and here is the rover path right here.